Good morning, everyone. I hope you're all doing well today. Just a reminder that our first midterm is next Thursday. So what I'm going to try to do today is going to try to cover some of these Serret-Frenet bases and then some of the friction force and spring force, time permitting, so that you can solve previous exams and get ready for the exam earlier. Again, the exam is on Thursday during class time. I'll send an email with more details about it in the weekend. Okay? So today we're going to learn about a new basis, which is the Serret-Frenet basis. So we know about the Cartesian basis, Ex, Ey, Ez. On Tuesday, we learned about which basis? The polars, which is 2D, and the cylindrical polars, which is 3D. Er, E theta, Ez. And today we're going to learn about these Serret-Frenet bases. So consider a particle in three-dimensional Euclidean space. Consider a particle tracing a path in three-dimensional Euclidean space. This is a bad color. I can write the position vector of the particle in Cartesians as R Remember, we also previously defined the arc length coordinate S. Okay, so recall that we previously defined the arc length coordinate as using this definition. ds by dt is the magnitude of dr by dt. So dr by dt is equal to the velocity, right? And we use the chain rule. We can write this as dr by ds by dt. I'm going to put a hat on the r because now I'm using the coordinate s to parameterize r rather than time. So here r is parameterized by time, here r is parameterized by s. And the ds by dt, which is the magnitude of the velocity, what did we call that? The speed, exactly. So that's v, the speed, dr by ds. There are no dots here. And what do we remember? Do you remember anything about the dr by ds vector? That's a vector, right? What do we know about it? It points in which direction? dr, which is, or in the same direction as the velocity, which is tangent to what? The curve, right? And what is its magnitude? 1. Remember, we drew this. I have a curve, I have r of t or r of s, r of s plus delta s, and I can draw delta r between them. And delta s is this length. So as delta s goes to 0, the magnitude the magnitude of delta r becomes equal to what? Which is the magnitude of dr becomes equal to what? ds, right? Okay, so, and the direction of delta r becomes tangent to the curve. Okay, so this dr by ds vector is a unit vector that's tangent to the curve. What did we call it? The dr by ds vector is a unit vector which is tangent to the curve. What did we call it? We gave it a name in the first lecture. Does anyone remember? Not quite. It's a unit vector which is tangent to the curve, so it's the unit tangent vector. We call it the unit tangent vector, which is ET. Okay, so let's repeat. What do we have so far? We have a particle moving in three-dimensional space. We want to introduce a new basis other than the Cartesians, other than the cylindrical polars. Today we're introducing the Serret-Frenet basis. So we have a particle that's moving in space, and I'm going to start by writing the velocity of the particle, v, as the magnitude, the speed, along ET, unit vector along the direction of the particle. So that's the velocity of the particle. Any questions so far? It has magnitude v and direction, unit direction ET, which is tangent to the curve. Any questions so far? Questions? Yes? Three-dimensional Euclidean space, which is, yeah. So this is like a mathematical space describing 3D. Okay, any other questions? Questions, yes. Yes, good question. So the hat is just to differentiate r from being expressed in terms of time versus in terms of arc length. Okay, so the hat means that this function is written in terms of arc length. Let me give you an example. Say there's a function that gives me the speed of the car, right? But one function takes in the time in minutes versus the other function takes in the time in seconds. So it's still giving you the same speed of the car, but the input is different. So I'll name them a little bit differently. I'll put one with a hat, one without the hat, for example. So the input is different, but they're equivalent somehow. Time in seconds and times in minutes is equivalent, and the output is going to be equivalent for equivalent. The output is going to be equal for equivalent inputs. Okay, but to differentiate the function, I'll differentiate it with a simple, for example, the hat, the tilde. Any other questions? Questions? Okay, so the Serret-Frenet basis has the first unit vector, which is ET, the unit tangent vector. How do we draw it? It's a unit vector in the direction of the velocity. That's ET for the Serret-Frenet basis. Does ET, does it depend on the location of the origin? Where I take my origin to be, does that change what ET is? No, it doesn't, right? ET, in fact, only depends on the curve and in which direction I'm tracing the curve. So ET only depends on the curve, and that's going to be the same for all the other unit vectors for the Serret-Frenet basis. The Serret-Frenet basis depends on the curve and in which direction you're tracing it, but it depends on the curve. It does not depend on the origin. Versus, remember, in polars or cylindricals, was the origin important? The choice of the origin important? Yes. Depending on where the origin is, the basis is going to change. For example, if I'm using the polar basis, if my origin is here and my particle is here, let's do the 2D polar basis. If my origin is here, my particle is here, this is ER and this is E theta, if that's EX and that's EY. Now, if I move my origin and I put it here, same EX, same EY. Now, if I draw my polar basis from this origin, call it O prime, this is ER prime, and this is E theta prime. So you see, for the polar basis, the location of the origin changes the basis, right? That's not the case for the Serret-Frenet basis. For the Serret-Frenet basis, no matter where the origin is, ET is tangent to the curve. Okay? So it really depends on the curve. Does that make sense? Okay. So I want to be able to write F equals ma, to do kinetics, to write F equals ma in the Serret-Frenet basis. So I need to find what the expression of the acceleration is in the Serret-Frenet basis. Remember, in cylindricals, we had A is r double dot minus r theta dot square ER plus r theta double dot plus r dot theta dot E theta. So we had this expression of the acceleration polars. We want the same expression in acceleration, but for the Serret-Frenet basis. Oops. I'm too strong. Okay. So I want to calculate the acceleration. How do I calculate it? Do you know how to do this? What do I do? What do I do? I take the derivative of the velocity, exactly. V dot, which is using the product rule, V dot Et plus kappa, V dot Et plus V Et dot. So that's the acceleration, the derivative of the velocity. Now I need to figure out what Et dot is. Okay? Now what does it mean, Et dot, so far? It's the time derivative of Et, right? So again, I have the curve. I'm tracing the curve. I have the particle that's tracing the curve. I can draw, the particle is here, then it moves here. I can draw Et and Et at time t, Et at time t plus delta t. I can put these at the same, starting at the same point, and I can calculate delta Et. Now delta Et by dt, the limit of that at z equals to 0 is Et dot. So what does Et dot mean? It's the rate of change of this unit vector Et. Is Et dot going to be 0? Raise your hand for yes. Raise your hand for no. Why not? Can you think of an example where it is actually 0? Yes. Exactly. When you're moving on a straight line, the direction is not changing, so Et is going to be, Et dot is going to be 0. But otherwise, it's not. Is it going to be a unit vector? That's a more difficult question. So Et is a unit vector, but its rate of change, is it going to be a unit vector? You can think of other unit vectors you know, and their derivatives. Are their derivatives also unit vectors? Discuss with your neighbors, because I see some shakes and yes and no's. What do we think? Is Et dot a unit vector? Any good explanations? Anyone? Let's take a vote. Who thinks it's a unit vector, Et dot? Who thinks it's not? Okay. Why? Can you think of any? What unit vectors did we introduce on Tuesday? ER and E theta, right? What is the derivative of ER? Theta dot E theta, right? Is that a unit vector? No. What is the magnitude of theta dot E theta? Exactly, which is not necessarily 1, right? So that's an example where the derivative of a unit vector is not necessarily a unit vector, because the derivative of the vector doesn't only have to do with the change in magnitude, which here it's always 1, so the magnitude of the unit vector is not changing. It also has to do with the change in direction of the unit vector, which makes that the derivative of the unit vector is not necessarily, doesn't necessarily have a unit magnitude. Okay? Any questions? Okay. I'm going to use the chain rule again, and I'm going to write et dot as det by ds by dt. And I'm using the hat here. What is the ds by dt again? The speed, right? Okay. So now we're going to learn a trick that will help us determine the direction of the et by ds. I'm going to start by saying that et is a unit vector, right? So what is et dot et? Since et is a unit vector, what is et dot et? 1, right? So what I will do right now is I will take the derivative of both sides of this equation with respect to s. What is d by ds of 1? 0, right? Does not depend on s. What about the derivative of the dot product with respect to s? How many terms is that? How do I take the derivative of the dot product? Yeah, I have to use the product rule, right? So that's det by ds dot et plus plus et dot det by ds is equal to 0. And the dot product is commutative, so I can switch. I'll get that 2, I'm continuing here, 2 det by ds dot et is equal to 0. I can cancel out the 2. And from this, I get that et is perpendicular to det by ds. Okay. Take a minute. Make sure your neighbor understands this. You're going to be held accountable. So if you have any questions, let me know. Your neighbor is in front of you, back, front, everywhere. Any questions? Yes. Like this. This is just a trick to figure out that et is perpendicular to det by ds. So I wanted this result, so I started with this expression, which is true, right? It is true. Yeah. Other questions? Questions? Okay. So then et is perpendicular to det by ds. Okay, so now we know something about the direction of et. Now, can we figure out something about the magnitude of ET? Okay, so again, we started with the fact that the velocity is equal to the speed along ET. I want to calculate the acceleration. The acceleration involves this ET dot, which involves the dEt by ds. So far, I know that dEt by ds is perpendicular to ET. Now, what do I know about the magnitude of this vector? Let us do this. Let me consider a curve like this and a curve like this. Okay? I'm going to consider a delta S the same on both curves. Almost. And I'm going to draw ET at S, ET, S plus delta S for this curve. And I'm going to draw ET at S, ET at S plus delta S for this curve. Do you see where I'm going here? I want to compare delta ET for both curves. I have the same delta S, so if I compare delta ET, I'll draw the two vectors here. That's delta ET. And here, that's delta ET. Delta S is the same. So then, from this, what do we know about the magnitude, or what can we infer about the magnitude of delta ET or dEt by ds? What does it depend on? Yes? Yes. Do you have to say anything?
I was just going to say, like, the magnitude of the curve.
Yeah, yes. So this quantity is how much the curve curves. We call this the curvature of the curve. So the more the curve resembles a straight line, the less dEt by ds is. Versus, as the curvature of the curve increases, in these two situations, which curve has the highest curvature? This one, right? So V as the curvature of the curve increases, dEt by ds increase. Okay. Any questions? So what we're going to do right now is we're going to define dEt by ds. The three, this equal sign means that it's a definition. That's equal to kappa En. Okay? En is the unit vector that is perpendicular to ET. That is the direction of dEt by ds. And kappa is called the curvature. Okay? So dEt by ds, I figured something about its magnitude is proportional to the curvature, which I will call kappa, and its direction is perpendicular to dEt by ds. So I define this direction to be En, the unit normal vector, which is perpendicular to dEt by ds. You might have heard of the radius of curvature. which is 1 over kappa. That's the radius of curvature. Okay? Great. Questions? Questions, questions, questions? Remember what I wanted to find initially was the expression for the acceleration A in this Serret-Frenet basis. So if I go back to A here, A becomes equal to V dot Et plus V Et, plus V Et dot. Et dot, which is V dEt by ds, and dEt by ds, which is kappa m. So I'll get that A is equal to V dot Et plus kappa V squared m. That's the expression of the acceleration in the Serret-Frenet basis. And since we want to complete the spaces, we will introduce the last unit vector of the basis, the unit binormal. EB is defined. Can anyone guess how EB is defined? So it needs to complete the right-handed triad, ET, EN, EB. So how is it going to be defined? Cross product of which two vectors? ET and EN. It completes the right-handed triad. Okay? And this is just an orthonormal basis. So as I have a vector that I can express in Cartesians, Vx Ex plus Vy Ey plus Vz Ez, and I can express it in polars. I can also express the same vector in the Serret-Frenet basis. Does that make sense? Any questions? What do you mean?
Can it be used for position?
Yes, because the position vector is a vector, right? The position vector is a vector, so technically you can express it in any basis. However, unlike Cartesians and polars, where V is x plus y plus z or V is r plus z, there is no one prescription for the position vector in the Serret-Frenet basis. There is not one. Usually we start with the velocity and acceleration. We'll do a few examples where we will relate the Cartesians and the Serret-Frenet basis, or the polars and the Serret-Frenet basis for a particular problem. However, these relationships depend on the problem. Actually, what they depend on, what the Serret-Frenet basis depends on, is the path, the curve that's being traced. Yes, so we'll do some examples and you'll see. Okay, but before that, what I'm going to do is I'm going to take, since the Serret-Frenet basis depends on the curve, I want to take some curve. And I want to draw the Serret-Frenet basis at different points on the curve. So let's take, the particle is going like this along the curve. I want to draw the Serret-Frenet basis at different points along the curve. Okay. So I will start with the unit tangent vector. How do I draw ET? It's always tangent to the curve, right? So ET we have a problem at a certain point. Which is it?
The corner.
Yes, here. At this corner, it is not well defined, right? Why? Because ET by definition is equal to what? We should have it on the board over there. ET by definition is what? dr by ds, right? And then r is not differentiable at this kink corner. Questions? Okay. Now I want to draw the unit normal vector En. So En is always going to be in the plane of the motion, right? V is always parallel to Et, and the acceleration is always going to have En and Et components, Et and En components. Also, En is going to be perpendicular to Et, right? So En is going to be in this plane of motion, and is going to be perpendicular to Et. So it's going to be either pointing up or down, perpendicular to Et. Which direction do you think it's going to point? En. Where? Up or down? Down. Why? Yeah, in the direction at which Et is curling, right? En is the derivative of Et, dEt by ds. So Et is always going to curl inside. En, we say that En always points towards the center of curvature. Okay. One way to think about it is that whenever I have a curve, if I take a point on the curve and a point before it and a point after it, these 3 points, if they're not collinear, they're going to uniquely define a circle. They're going to uniquely define a circle, which we call the osculating circle. Notice that, okay, let's wait. This is called the osculating circle. So whenever I have a point on the curve, this point defines an osculating circle. One way to think about it is that the circle, it passes by this point and is tangent to this line. Another way to think about it is that the point before it, the point after it, 3 points, they define a circle. This is called the osculating circle. The center of the circle is called the center of curvature. And the radius of this circle is called the radius of curvature. Remember where rho is 1 over kappa. So as the line is more flat, does that mean that the radius of curvature is more or less? as the line, or as the curve becomes flatter, what happens to the radius of curvature? Does it increase or decrease? Increase, right? For a straight line, what is the radius of curvature of a straight line? Infinity, right? So as the curve becomes flatter, the radius of curvature increases. So rho increases, kappa decreases. So you have less curvature. As the curve has more curvature, for example, if I have here, so this is the oscillating circle here. The radius of curvature is less, the curvature is more. Where does En point at this point? Towards the center of curvature. So En is always going to point towards the center of curvature. Okay? So at this point here, where does En point? Downwards. En here, like this, right? What about here? Show me your fingers. Yeah. Here, En here, En. Okay. What about on the straight line? On the straight line, En is not uniquely defined, right? Because there's no, well, what is En by definition? En is kappa det by ds. For a straight line, kappa is 0. So En is not uniquely defined. Det by ds is 0. Okay? In the case of a straight line, what we do is that we just choose En to be perpendicular to ET, but there are some smart choices. We're going to do an example. Okay, so there's that. Any questions so far? Are we kind of getting this? Let me say like 80% getting this. Raise your hand. Kind of. If you're not, then should I re-explain somewhere, anywhere? Questions? Yes?
So could you explain how, is kappa something we can calculate, or is that something we get as a result of the other direction where we already have the derivatives and then we calculate kappa from that?
Good question. Kappa is something we can calculate from geometry, from the curve. Yes, and we're going to derive an expression for kappa for plane curves next week. You're welcome. Good question. And we're also going to do an example where we have some position velocity acceleration that we can calculate kappa. Any other questions? Yes?
So are you choosing the vector En and another vector that's perpendicular to ET?
No, just En. So here, wait, so do you mean the unit binormal is also perpendicular to ET?
She's like reading the description. Choose En and.
Sorry. Choose En that's perpendicular, a vector perpendicular to ET. Sorry. Yeah. Okay. Thank you. So En, let us notice that En between here and here, En flipped directions. Why? What happened in between? Yes? Exactly. There was an inflection point here. So at the inflection point, also det by ds, which is d by ds of dr by ds. So what's the inflection point? It's when the second derivative is equal to 0, right? So here, at the inflection point, the second derivative is equal to 0 of the curve. This means that det by ds is 0. So En is also not uniquely defined at inflection points. So at the inflection point, just before En is this way, just after En is this way, at the inflection point, it's not uniquely defined. Okay? So points, where did I put that? For a straight line and at inflection point. En is not uniquely defined. Okay? Now we still need to add one vector to complete the triad, one unit vector to complete the triad, which is what? The unit binormal, right? So what is the unit binormal here? I have to do the cross product. So where is it going to point? Into the page, right? I'm doing the right-hand rule, and EB points into the page, still here, until I flip here, right? And here I flip, and then here I flip back, right? ET, EB. And this portion of the curve is not uniquely defined. Say I take En to be like this so that it's continuous. Say I take En to be like this so that En is continuous. Then EB is going to be inside or outside the page? Inside. Okay, cool. Any questions? Yes? Yes, yes. So whenever I have a curve, if I have, 2 points that uniquely define a line, 3 points that uniquely define a circle if they're not collinear. So whenever I have a point on the curve, the point before it, point just after, they define a circle. This circle I call the osculating circle. Another way to think about it is that there's only one circle that passes by this point and is tangent. Well, no, let's keep the 3-point definitions. Okay. So 3 points define a circle. That's called the osculating circle. The radius of the circle is called the radius of curvature. The center of the circle is called the center of curvature. And as the radius increases, the curve becomes flatter. So the curvature decreases. And as the radius increases, it becomes flatter. So it becomes more like a line. Curvature decreases. And the opposite happens when the radius increases. Questions? Yes?
Can you just go over again which finger represents which unit vector for the right-hand rule?
Yes, it's the same order as EX, EY, EZ, right? ET, EN, EB. As long as you have the same cyclical order, it doesn't matter which one is which. So the cyclical order is ET, EN, EB, or you can do ET, EN, EB. It depends on how you learned it. What I usually do here is that curl my fingers from ET to EN, and my thumb points towards the third. Any other questions? Okay. So unfortunately today the printer was not working, so I'll need you to pull up the set on your iPads, laptops, computers, phones. So let us do set 7. Start with problem 7. Set 7, problem 7. Maybe I'll try to project it on the board. Oops, that's not connected. So take a couple minutes, start with set 7, problem 7. Things are too messy here. Okay, here. Okay. So you cannot see my screen, right? HDMI, projector on.
You connect the HDMI cable to it. It won't work with the C-type, I think.
Oh, it will not.
Yeah.
Ah. Oops. Okay, great. Let's look at a few animations. Thank you, Megana. So this is a particle moving on a random 3D curve. And this is the oscillating circle as the particle moves. So the red vector is which vector? The red vector, En, right? Which one is Et? Blue, and then Eb is the green. So these vectors are linked, and then these videos are linked in the notes. You can check them. Does that help clarify things? This is another example here. Which vector is Et? Blue. And you see, as like in this portion of the curve, the radius becomes large because the curvature is low. En is which one? Green, and the binormal is the purple. You're cheating. Were you looking here? Okay. So,
Has anyone actually made it
now
to
we
level
have a.
4 before? If you're slightly congested, use level 1.
Before he'd become the first American in half a century to win a world title. Now he was lying in first place at Whistler and chasing Olympic glory. After the first 2 runs, the Americans have built a lead of nearly half.
Okay. This is my attempt at this, but does this make sense? It's a bobsled competition. Et is changed to the curve. En is pointing towards the center of curvature. So you can think of the circle, the oscillating circle, it's almost horizontal at this point. And Eb is such that Et cross En is equal to Eb. Yes? Not quite. We'll talk more about the Coriolis acceleration when it comes to rigid bodies. Yeah. Okay. Okay, here. How should Et point? Change the curve, right? So Et, well, I cannot, Et tangent, and then En, how is it pointing? It's kind of pointing upwards, right? Versus before, when the path was almost horizontal, when the circle was almost horizontal, the En was pointing inwards. Versus here, it's pointing upwards. So this is kind of my attempt. Et towards the front, En, and then Eb is completing the triad. And you can think of how this space is going to change as, like here, for example. Here, En is, how is it pointing, En? It's horizontal, right? Like kind of Et and En are horizontal, and then Eb is pointing up, almost.
On the course at speeds of up to 140 kilometers per hour. Now the drizzly weather made the track a little slower than it had been on the previous day.
Okay, I think that's enough. So here, this is problem 7. Okay, so I will need to copy this problem, and I need to write it on the board. Okay, yeah. too distracting, I'll remove the projection. Okay. And these points they were called, okay. So the slider is coming this way. And I have points A and B. This is a semicircle with radius, call it R. And okay, so the 120-gram slider has a speed, V is 1.4 meters per second. Okay, as it passes point A, so that's at A, which lies in the horizontal plane, so gravity points vertically down like this. Which lies in the horizontal plane. Determine the magnitude R of the force which the guide exerts on the slider just before it passes point A and as it passes point B. Okay. So we want to determine the force that the guide exerts on the slider throughout its motion, in particular before A and after B. So I need to determine the force that the guide exerts on the slider. I'm going to follow the 4 steps. Okay? Okay, so step 1, I will set up the Serret-Frenet basis. Now in this problem, since it's a particle moving on a circle, the cylindrical polar coordinates and the Serret-Frenet basis are equally, as easy or equally as difficult, but we're going to practice using the Serret-Frenet basis for now. So a particle is moving like this. Let me draw the Serret-Frenet basis at these 2 locations. So at B, how do I draw ET? Up. What about EN? Inside. Okay, just after A, how do I draw ET? Like this, and EN like this. Right? Now, just before A, the Serret-Frenet basis, well, ET is unit tangent just before A. So they're the same. EN is not uniquely defined because it's a straight line. However, the smart choice would be here to define EN which way? Up, right? Exactly. Why? So that EN does not jump as I'm going from before A to after A. So that's my Serret-Frenet basis, and V is going to be equal to VET throughout the motion. A is going to be equal to V dot ET plus kappa V squared EN. What is kappa here? 1 over R, right? For the straight portion of the curve, what is kappa? For the straight portions of the path, kappa is 0. And then for the circular portion of the path, what is kappa? It's 1 over the radius of the osculating circle, which here is the path itself because the path is circular. So what is kappa? 1 over r, right? I'll call it capital R, which was 0.2, 1 over 0.2. Okay, any questions so far? So that was step 1. Step 2, we want to draw the FPD of the particle. Okay, what are the forces acting on the particle throughout its motion? I have the weight. So here the particle, the weight is going to act into the page, right? Inside the page. So then is it along which unit vector is the weight? Force. Easy. Well, let's use the Serret-Frenet basis. Here, the unit binormal points outside or inside the page? It's outside. Raise your hand if you agree with EB pointing outside. Okay, cool. Questions? So then the weight is pointing inside the page, right? So it's along minus EB. Weight is mg along minus EB. Okay, what other forces are acting on the particle? The normal force. What is the direction of the normal force? Mm-hmm. What is it? Positive EB. Right, exactly. So the normal force does have a component along EB, but is that it? Is that it? And another component along EN. This is very important. That's a very important point. Whenever you have a particle moving on a curve, the normal force is going to have two components. Think about yourself being on a roller coaster, right? If you're on a roller coaster, what are the normal force directions acting on you? Two. One of them along EB, so that you don't fall downwards, right? And the other so from the seat from below, and the other normal force components from the sides of the roller coaster. So whenever you have a particle that's moving on a curve, the normal force has two directions, two independent directions, which is what's happening here. There is a normal force component that's counteracting the weight, so the particle cannot go down, and another normal force component that's enforcing that the particle is moving on a circle and not straying away from the path. Another way to think about it is that the particle is moving on a curve. Now it has how many degrees of freedom? If the particle is moving on a set curve, so a particle moving in space has how many degrees of freedom? 3. A particle moving in a plane, 2. A particle moving on a curve, 1. So 1 degree of freedom, how many constraints? 2, right? How many constraint forces? 2. That's another way to think about it. Okay. So we have two normal force directions. When we learn about friction, there might be friction. In which direction would friction be if this surface is rough, if this guide is rough? Along ET, right? Along ET. Not along the normal directions, but along the direction of motion, which is ET. Yes?
I'm curious why we package EB and ND into normal force instead of just making it another force and writing it separately.
Oh, that's fine. That's a notation thing, which you can do. I don't mind. However, later on when we learn about the friction force, hopefully in a few minutes, if we have time today, the friction force is going to, for example, if it's kinetic, it's going to be proportional to the normal force. So you have to take into account both components. Yeah. Okay. Questions? Yes. Right, so the free body diagram is just that I have the particle. So this is not my best depiction. I cannot actually draw N very nicely. So the way I do it is I draw N randomly, and then really what I look at when I grade is this prescription of the normal force, that the normal force has components along En and Eb. Again, imagine you were on this rail. You would need two forces to keep you going on the rail. One force is sideways so that you keep going on the rail, and the other force is from below so that you don't fall down. So the normal force has two components plus the weight is pulling you down. Right? Does that make sense? Questions? Questions? Okay. So step 2 was drawing the free body diagram. Yes?
Wait, the normal force, the component of the normal force in the EN direction, would it be 0 in the straight portion?
Yes. But we will solve for this using the balance of linear momentum, which we'll do right now. Okay. So step 3, notice the same steps, no matter what the basis is, as long as we're doing a kinetics problem. Kinetics between forces. Okay. F equals ma. So now we have mg minus mg eb plus nen is equal to m right? And now I can project. Okay, so raise your hand if you're okay with my projections. You can take a minute to think. Questions? Questions about them? Yes? Why would it be negative? Well, so En is pointing towards the curve, right? What the particle is going to tend to do, if the particle is tracing a circle, because of the centripetal acceleration, the particle is going to tend to accelerate outwards, outside the circle. So the normal force comes and pushes it in. That's why it's inside. That's kind of the physical intuition, but mathematically that's the result. And n is positive along En. This component is greater than 0. So think about this. Think about it this way. If I have this water bottle and I tie it to a cord and I'm turning this way, if I release the cord, in which direction will the water bottle go? Towards me or outside? Outside. Okay, so the tension force needs to pull the water bottle towards me so that the water bottle keeps going in a circle. And the same thing is happening here. The normal force is always going to be towards the center of the circle. Any other questions? Yes?
Can you remind me why we put a dot next to all three of the E's?
Oh, that means that's my notation to say that I'm projecting along EB, EN, and ET. Remember, because projections are dot products. What does it mean mathematically that I'm projecting this equation along EB? I'm taking the dot product of every term in the equation with EB, then EN, then ET, to get scalar equations. Any other questions? Okay, great. What can you say about the speed of the particle as it traverses the path? Right. Okay. So the binormal component of the normal force is always going to be equal to mg, but this component of the normal force along n, that's going to vary, right? On the straight portion of the curve, what is the normal force along En? 0. And what is the normal force along En on the curved portion? M kappa v squared is kappa is 1 over r. So let me look at this. At A minus, the normal force is equal to just mgEb, right? What do I mean by A minus? Just before A. Okay, at A plus, that means just after A. The normal force is going to be equal to the normal force at A minus. The normal force at A plus is going to be equal to mgEb plus m kappa, which is r v squared En, right? So just before B and just after B, the normal forces are different. So what happened to the normal force at A? It jumped. We have a mathematical notation for this. The jump of the normal force at A. This means jump. By definition, it's NA plus minus NA minus. So, and it's going to be here equal to m over r v squared En, which is different than 0. So the rate of a change, I'll let you take a minute to absorb this. Any questions? So I just calculated the normal force before A, just the normal force after A. I'm trying to make a point here about jumping forces. The jump in a force, that's called a jerk. And that's not a good thing. That's a sudden change in force, and that's not a good thing. So the particle is going to experience a sudden change in force. Sudden change in force when it transitions from the straight portion to the curved portion of the path. Does that make sense? Let's drive the point in a little bit further. Let's consider a roller coaster. Let's consider a roller coaster that's formed of a straight line connected to a circle. That's supposed to be a circle. Okay. A straight line connected to a circle, and then a straight line. Can you comment on the safety of this roller coaster?
Very unsafe.
It's very unsafe. Why? You can discuss, take a minute, discuss. Why is this roller coaster unsafe? And while you're discussing, take a minute and look at actual roller coasters. Google photos of roller coasters and check, how do they look like? Are they circles or do they look like something else? Okay, then, what do we think? Is this roller coaster safe? Yes or no? Why is it not safe? And I'm assuming there's enough kinetic energy so that the people are not going to fall off when they're at the top. But yes.
Because of
The
the jerk.
jerk, where exactly?
Well, it would be 2 points if you did the whole loop, but the first point is like right.
Exactly. So that's when you're transitioning from the straight portion to the curved portion, right? There's going to be a sudden change in curvature, which is going to cause a sudden change in normal force, which is going to cause a jerk. Might be big enough to break your neck. Okay, so that's bad. Even when roads are being designed, they're designed in such a way so that the curvature increases kind of linearly. You don't want a sudden jump in the car, right? So that's why roller coasters are usually not circles connected to straight lines, but they're clothoids. They look like this. So zero curvature, linearly increasing, and then at the top, maximum curvature, and then decreasing, and then linearly decreasing goes back to this. So this is called a clothoid or an Euler spiral. So this shape has linearly increasing, then linearly decreasing curvature. So there's no jerk. There's no sudden jump in curvature, right? Do we see why the clothoid is safer than the circle? Okay, great. Any questions? Okay. Let's do question 5 in the same set. And I don't think we'll be able to explain friction today, but we'll explain the spring force. So question 5, then spring force, we will see. Okay, let's do question 5 first. Let me erase the board. Okay, and this one is easy to copy because there are no figures. A particle which moves with curvilinear motion has coordinates in meters which vary in time t seconds according to x is equal to 2c squared plus 3t minus 1. And y is equal to 5t minus 2. Determine the coordinates of the center of curvature C at time t equals to 1 second. Okay, take a couple minutes, try to come up with a strategy for this. Chat with your neighbor. We need a strategy. We need to determine the coordinates of the center of curvature. We're kind of given the path of the particle, right? Okay. Yes. Calendar. Yeah. Scroll up. Okay, so ideas, what do? I want to determine the coordinates of the center of curvature. What do? You had your hands up?
First,
Right.
So you take the derivative of x and y.
Okay, this I can do. I can write the position vector of the particle. Where x is this and y is this, and v is x dot, which is 4t plus 3. Plus 5, sorry, y. Right? This I can do. What else? I want to determine the coordinates of the center of curvature. Which equation contains the center of curvature? The expression of the acceleration, right? So this acceleration, I can write it in the Serret-Frenet basis as v dot et plus kappa v squared en, right? So technically, if I take the dot product of this equation with en, I will get 4 ex dot en is equal to kappa v squared. Where I know the speed, right? I can calculate the speed. So this quantity is known. Kappa is what I want to find. And to be able to find kappa, all I need to know is what? Et dot en. Sorry, ex dot en. So that I need to determine the Serret-Frenet basis in terms of the Cartesians. How do I start? How do I find en? Well, let's go step by step. Can we find et first? How do I calculate et? Yes. Yes, the velocity over its magnitude, right? So that's going to be 4t plus 3 ex. So that's et, which I can replace at t equals to 1. The square root of 49 plus 25 is 4, as 49 plus 74. Yeah. Okay, I found et. How can I find en? Well, first, any questions? How do I find en? Yes. Right. That's actually the easiest way to find en, right? So I have that et cross en is equal to eb, right? So et, en, eb is an orthonormal basis. I can flip. I can say that en, this is equivalent to saying that en is eb cross et. So as long as I'm going cyclically, I'm maintaining en is equal to eb cross et. So et I know, right? Et I know. eb I also know. Because this motion is in the plane, what is the direction of eb? Ez, well, it's plus or minus ez. We need to figure that out. Plus or minus ez to be determined. So what I'm going to do is I'm going to consider my xy basis. Well, whatever the curve is, the particle is tracing. I can draw the acceleration at this instant. The acceleration is going to be equal of the particle is going to be equal to 4ex, right? That's the acceleration. I can also draw et, which is equal to this. Et, which is going to have positive and x and y components. Et. With me so far? Take a minute, make sure your neighbor is with me so far. And then if you're with me, draw En on the figure. How will I draw En? It's perpendicular to Et, right? Down or up? En down or En up? Down? Who says down? Who says up? Discuss. There's a discrepancy here. Is it down or up, and then why? Because we're not guessing here. Okay, so any answers? Is it pointing down or up? Yes.
We could say it's down because if we take A, kind of, if we project A onto ET, and then we take the part that's not the projection, I don't know what you'd call that, just the arrow down, then that means it has to be down that way.
Very good. Very good. En needs to be down. Why? En needs to be down. Why? Because what is the expression of A? A in general is V dot Et plus kappa V squared En. So if I calculate A dot En, that's equal to what? Kappa V squared, which is always positive. So the dot product between A and En always needs to be positive. So the angle between A and En needs to be acute, needs to be less than 90 degrees. Or else the dot product will be positive. It will be negative, which is not possible. So En is always such that A dot En is positive. So En needs to point down. Does that make sense? Questions? So how is EB then? Into the page. EB now is equal to not plus but minus EZ. So now I can calculate En is equal to minus EZ crossed with this. So what is EZ cross EX is EY. Did I do my cross product correctly? En negative EY covered positive En. Oh, okay. Questions? Then coming back here, now that I know what En is, what is Ex dot En? Right, it's 5 over radical 74. 4 times 5 over radical 74 is equal to kappa V squared, which is the magnitude of the velocity, which is 74. Yeah. So I can find the radius, the curvature and the radius of curvature. One more point remains. How do I find the coordinates of the center of curvature? So we now know what the radius of curvature is. How do I find the coordinates of the center of curvature? You might want to sketch this. Sketch a curve. Take a point on the curve. Where is the coordinates of the center of curvature going to be? So if I take a curve, I have a point on it, whatever, point on it. I can draw the oscillating circle, and that's C, the center of curvature. How can I find the coordinates of C? Well, En is which vector? It's this, right? En is a unit vector like this. And then this vector is equal to rho En, which is 1 over kappa En, right? So if I want to determine RC, that's equal to what? What do we think? What do we think? So this vector RC from the origin to C is equal to what? We're very close. It's going to be equal to what? The sum of two vectors, which are yes. En times RC, no. Because how would you multiply vectors, right? What is this vector here? From the origin to the particle? R, right? Which is xex plus yey, right? So what is the coordinates of R? What is the position vector of RC? RC is very simply what? R plus rho En. That's the position vector of RC, right? This orange vector is the sum of the purple plus the yellow. I found the coordinates of the center of mass. Oops. So that's a very interesting problem, right? Make sure to solve it again on your own. Any questions? Yes.
In this case, would rho En be subtracted?
What is it? You're adding two vectors. This one plus this one give you the orange one. Yeah. Any other questions? Questions? Okay. What is it? Wait, question. Who can answer this? Where can we get R, the position vector of the particle? Yeah, the position vector is given. It's xex plus yey, where x and y are given as a function of time. So you can find it at t1 or at any time, right? You're welcome. So this animation that you saw, the animation that I saw, was created by a student like you who took the class. So what did they do? They chose a random curve, and using these steps, they calculated ET and En and the radius of the oscillating circle and the center of it. So they were able to plot all of these quantities that way. You can do this problem at t1 or at any time. Anytime you can go through time, you can animate the motion. Any other questions? Okay. Okay, we have 20 more minutes. Shall we do spring force or friction? Let's start with friction, okay? By the way, I do have videos about spring force and friction, so if you wanna, jump ahead, you can for the sake of the midterm. Okay, so let's start with friction. what I want to try to do right now is I want to come up with a model for friction. We want to try to come up with a model for friction. So look at this eraser here. If I push it with some force P, what is the model? I'm trying to do an experiment, and I'm trying to write equations that describe the experiment. So this is the experiment I'm doing. I have my object on a surface. The object is rough, the surface is rough, right? This is not ice. When I push this, it will stop. It will not go on forever. So there is friction between the two surfaces. Okay. If I push this eraser by small enough force, will it move? No. So that's my first observation. So consider a block, and you're applying a force P onto it. If P is small enough, the eraser will not move. Okay? Then, and you can do this with your phone in front of you or something. If I keep on increasing the force at which the magnitude of P, what's going to happen? I'm going to initiate motion, right? At some critical value, okay, so again, I'm trying to find a model to describe friction in the real world. I'm doing an experiment to see to which I'm going to fit my model. Okay, so I push this with a very small force, it doesn't move. I keep on increasing the forces, that suddenly it's going to move. Okay. Once it starts moving, I need a constant force to keep it moving at the same speed, right? Once the block So once the block starts moving, a constant force is required to move it at a constant speed. Now what I want to do is I want to compare P star and P double star. So let's call this force P double star. That's the force required to move the block at a constant speed. P star is the force required to initiate the motion. Which one is greater? P star, right? P star is greater than P double star. The force required to initiate the motion is less than the force required to sustain the motion at a constant speed. Okay. One last observation I'm going to add is that if I increase the weight of the object, what's going to change? The force required to start the motion and the force required to sustain the motion, they're going to increase, right? Coulomb was a French engineer who made these observations. He made these observations and he proposed the following model for friction. So we're going to say what his model is, and we're going to see or verify that it actually describes these observations well. Okay. What Coulomb said is that friction has two types, a static and kinetic friction. So friction, it's static or kinetic. Okay. When is the friction between two surfaces static? When there is no relative velocity between two surfaces. So if I consider an object and a surface, I'm going to take this point, call it P. Take this point, call it Q. So when the surfaces are in contact, P and Q are in contact. I'm going to say that VREL, the relative velocity between the two surfaces, is the difference of the velocities of their contact points. VP minus VQ. If VREL is equal to 0, then friction is static. And if VREL is different than 0, then friction is kinetic. Okay, let's think of an example. If I have a box on a ramp, and the box is not sliding down, it's just sticking on the ramp, is friction static or kinetic between the box and the ramp? Static. Now, if the box is sliding down, kinetic. Okay? A common mistake people do is that they don't look at the relative velocity, they just look at the absolute velocity of the block. Can we think of a case where the block is actually fixed, but the friction between it and the surface underneath it is kinetic? Yes. Exactly. If I have like a box and a conveyor belt and I'm holding the box fixed and the conveyor belt is slipping, is moving underneath the block, then the friction between the two is kinetic. Okay? If I'm driving my car and I have a box in the trunk, is the friction between the box and the car static or kinetic? Static, in which case, if the box is not moving relative to the car. So even though in absolute sense, the absolute velocity of the block is not 0, because its slip speed, its relative velocity relative to the car, the surface underneath is 0, then the friction is static. If the car is sliding in the trunk, then friction is going to be kinetic. Okay? So it's not true that the friction has to do with the absolute velocity of the object. It has to do with the relative velocity of the object relative to the surface, the rough surface that's in contact with it. Okay? Now, static friction is actually an unknown, which you solve for. However, it does need to satisfy the static friction criterion. What is the static friction criterion is that the magnitude of the friction force, static, needs to be less than or equal to mu s times the magnitude of the normal force. Where mu s is some coefficient which we call the coefficient of static friction, some constant. Some constant that's determined experimentally. One common mistake people do is that they say that static friction is equal to mu Sn. That's not true. Static friction is an unknown which you need to solve for from the problem, but it has an upper bound. The upper bound is that it's less than or equal to mu Sn, right? So I can go back and think of my experiment. I'm pushing the block with a force P, okay? So let's say when the block is static, what are the forces acting on the block? Weight, normal, and the friction force. Okay? When the block is static, it's not moving, the friction force is going to be static. So its magnitude and its direction are both unknown. It's an unknown force. So all I know is that the weight is minus mg Ey. Normal force is Ney. Friction force is minus the friction force Ex. So it's just going to be along Ex. The friction force is going to be along Ex. So, you know, along the surface where you have sliding. And the P is Pex. So the block is static. I can write my F equals ma. What is the acceleration in this case if the surface under the block is fixed? If the surface underneath the block is fixed, then what is the acceleration of the block if it's still not moving? A is 0. A is 0. Then I can write that minus mg Ey plus Ney minus FFEx plus PEx is equal to 0. I can project along x and y. I'll get that N is equal to mg and the friction force is equal to P. Okay? So I have my block on the surface. I'm pushing it. As P increases, the friction force increases. But there's a limit, right? I cannot keep on increasing P forever and the block not move. What's the limit? That this is true as long as the magnitude of the friction force is less than mu Sn. Okay? Which means that P, which we call P star, P is less than mu S mg. That's when you don't slip. P star is the limit value at which you're going to slip. Mu S mg. Okay? Notice how static friction is an unknown. So when friction is static, the friction force is an unknown, but the motion is known because it's the same as the surface underneath. Whereas when friction is kinetic, it's the other way around. When friction is kinetic, the motion is unknown. You need to solve for the motion, but the friction force is prescribed. Okay, so the friction force is non-prescribed. It's equal to minus mu k, or it's equal to mu k magnitude of the normal force. So it's proportional to the normal force. Direction minus v rel over the magnitude of v rel. And you solve for the motion. Okay, so when the block starts to move, then the acceleration is an unknown, right? but the friction force, we have the same free-body diagram as above. The friction force is prescribed now. It's minus mu k. The normal force is the same, mg. And if it's going to go this way, then the direction of the friction force is minus ex. We can plug that into F equals ma. And you can obtain a differential equation for x double dot. Okay. So that was a quick introduction to friction. So friction is static and kinetic. Static is unknown. The motion is known, but the friction force is unknown. Versus when the friction is kinetic, then the motion is unknown, the friction force is known. Okay? And it's equal to this. When you have a problem, for example, if I ask you to calculate the motion of a block, if I ask you to calculate the motion of a block that's on a surface and you do not know if the block is sliding down, up, or just static, the way you solve this problem is you first assume that friction is static. You calculate the friction force to see if it satisfies the static friction criterion. If it does, then it's static. If not, then it's kinetic. So we're going to start on Thursday with this example, which is a problem in your problem set. If I have a block that's on a surface, how do I know if friction is static or kinetic, like the motion of the block, if it's fixed or sliding down or up? Well, you assume that it's fixed. You calculate the friction force, you see if it satisfies static friction criterion. If it does, then it's fixed. If it doesn't, then it's sliding down. Then you need to prescribe F, friction force, and solve for the motion. Thank you all for coming. It was a hefty lecture today, but hopefully it'll help you out for the midterm. Okay? So the midterm covers up to Serret-Frenet friction and spring force.
Was asking if he has to move his office hours because tomorrow is a holiday. Is it a campus-wide holiday or is it okay for him?
He cannot have, I don't think he can have office hours tomorrow. So
he said he wanted to have it because people are approaching. Is it okay if he moves it online? Like if students want to join? And one more question was regarding the online process.